Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Today we will discuss another important topic in distillation, optimization of distillation process. This course will be presented in two-part series. Part 1, conventional optimization methods. Part 2, optimization by heat integrated technologies. The course menu comprises 1. Introduction to optimization. 2. Conventional methods of optimization. And 3. Innovative technologies of heat integration. The learning outcome of this course is to learn the conventional methods of optimization applied at the design stage, to get an insight into heat integration technologies and distillation process, to develop engineering skills through case studies. When we think of optimization in any process plant, the first mass transfer operation that comes to our mind is the distillation process. Distillation is energy driven and energy intensive separation process. It currently consumes 40% of the total processing energy used in refining and continuous chemical processes. The economic optimization of distillation column to minimize the total investment and operating cost involves selection of number of trays, feed location, operating conditions, and heat integration in the process. For sustained savings in operating cost, you cannot overlook the factors related to stability of the control loops and the mindset of the operators. Tuning of the controllers in the process control loop needs to be given due attention. Likewise, it is the operators operating the DCS panel who, through manual interventions, adjust the deviations in the measured variables as and when they move away from the set point due to interruptions or variations in the process parameters. There is an inherent weakness in the dynamic behavior of the controllers. This causes the operator to make frequent adjustments in the process parameters. That's the reason the operators try to operate within a zone of comfort by keeping the operating parameters at a safer level than what is required to be. The optimization during the operating phase of the plant provides potential opportunities to increase throughput and increase profitability. This is achieved by improving process stability, better product quality, and flexibility in operating conditions. We will now discuss in this course about the optimization approaches in the operating phase of the plant. Our focus will be on optimization approaches followed in the design phase. We will now move on to part 1, optimization by conventional methods. Conventional methods at design stage. Several methods are used for optimizing distillation process at the design stage. These approaches include selection of right feed location, selection of optimum operating pressure, and feed conditioning. Take a look at this picture. Is the feed entering at the optimal location or tray? Is there a possibility to preheat the feed to the column? Or is the column designed for optimum pressure? We will move on to find out answers to these very relevant questions. First, selecting the optimum feed location. Selecting the optimum feed location is critical for maximizing distillation column performance. The feed location depends on the composition of the feed and the final purity of the product required. Ideally, it is recommended to introduce the feed where the feed plate composition matches the feed composition. This will cause minimum composition gradient between the feed and the distillation internal fluid on the feed plate. Introducing the feed at the wrong location causes the trays around the feed entrance to operate inefficiently. The degree of separation is decreased at the same reflux to boil-up ratio. In other words, higher reflux to boil-up ratio is required to maintain the required separation with column consuming excess energy than required as per design. Usually the column is designed for a specified feed composition. If the feed composition changes due to sourcing of feed from different suppliers or changes in performance of the upstream facilities, the column separation performance gets impacted. In such situations, process simulation modeling needs to be carried out to arrive at the new feed tray location. Multiple feed locations cannot be arranged in packed columns. This is due to the fact that the liquid is a distributed phase and no collector tray can be installed within a single bed. Key ratio plotting is another useful tool to evaluate Optimum feed location. The key ratio is usually expressed as a ratio of light keys to heavy keys. So how do we do that? The optimum feed location can be graphically plotted through a chart of key ratios versus the stage number. The optimum feed stage is that where the key ratio of the liquid or vapor, depending on whether the feed is liquid or vapor, is close to the key ratio of the feed stream. This will ensure that the feed composition is comparable to that on the stage, thus minimizing remixing. This type of plot is far superior to XY diagram for identifying mislocated feeds. This figure is an illustration of how we can use key ratio plot to determine the optimum feed location. Referring to the figure, the key ratio of the feed is approximately 1, as indicated by the blue color. The key ratio plot of the liquid on the stages is indicated in the red color. The optimum feed stage lies between 10 and 18. Now you can simulate the column and find that the optimum feed location for the lowest reboiler duty is at stage 17. Thus, by optimizing the feed tray, we are able to reduce the reboiler duty and thereby the operating cost. It should be noted here that the key ratio plotting only shows the binary key component behavior. Light non-key components are not recognized in this plotting. This should be taken care of for design of multi-component distillation. Now we will move on to another optimization parameter, selection of optimum operating pressure. High operating pressure means higher operating temperature and it reduces the vaporization. More energy is added to the reboiler at higher pressure than at lower pressure to get the same separation. Hence, it is necessary to optimize the column pressure to reduce the reboiler duty. Optimum value also requires that the column top pressure is sufficient enough to permit condensation of overhead vapor with the available utility. In many situations where cooling water is used as a cooling medium, the available cooling water temperature fixes a minimum operating pressure. The design point will fall between these two extremes. Determination of optimum pressure consists of construction of number of plate versus reflux curve for each specified separation and pressure. Figure 2 illustrates such a curve for a low pressure olefin column. Plate versus reflux curve clearly indicates the minimum number of stages and the minimum reflux required for separation. Illustrated in this figure is the effect of pressure on the reflux versus number of theoretical stages. It can be seen from the curve that lower pressure leads to lower reflux requirements. Alternatively speaking, for a given reflux ratio, lower pressure requires less number of theoretical stages. While considering revamp of distillation columns, optimization of pressure can be considered as one of the alternatives. But you must exercise care while attempting to do this. Lower pressure leads to hydraulic limitations for tray operation due to high vapor velocities that leads to flooding, jet flight. In such cases, the analysis of revamp involves comparison of effects of decrease of pressure on reflux reduction versus the effect of lower pressure on tray capacity. One of the options to overcome tray capacity limitation while attempting to optimize pressure is to use high capacity trays in place of conventional trays. For columns operating with the same overhead pressure, reducing pressure drop across the column can optimize energy requirement. This may be achieved by use of distillation trays or packing that has lower pressure drop. This permits the column to run at a lower overhead pressure with less reboiler energy. Now we will move on to another optimization parameter, feed preheating or pre-cooling. Feed preheating or cooling is an important external modification. It is less expensive compared with interheating or intercooling. Feed pre-cooling or preheating can be useful to unload the top or bottom section of the column. This figure illustrates how preheating or cooling is done in the column. Part of the cold feed is preheated and admitted to the tower at few trays below compared to the original feed tray with feed without preheating. Cold feed may require a large amount of heat exchange below the feed stage to strip the light components. Preheating part of the feed reduces the heat load in the stripping section. Using a process simulator, optimum split ratio and feed location can be obtained. We will now walk you through an exercise on the impact of changing operating parameters in the column. Let us consider propane and propylene splitter in a refinery. The objective of the optimization is to reduce the utility cost by using optimal reflux quantity while maintaining top and bottom products quality. This figure illustrates the propane and propylene splitter for our case study. Propane and propylene mixture is a feed. Propylene is the distillate product and propane is the bottom product. Cooling water is the utility for the condenser. Heat duty for the reboiler is provided by steam. Select any process simulation tool such as ChemCAD, Pro2 or Aspen Plus. Create the flow sheet. We need one inlet or feed stream, two outlet product streams with a distillation column. Select the column type with a condenser and a reboiler. This figure is the operation flow sheet for the simulation. The column consisting of 241 trays with the feed entering at 156th tray. The condenser is a total condenser and the reboiler is partial liquid product. The column variables are pressure and temperature. Operating parameters include three variables. They are feed flow, distillate flow, and bottom flow. This table shows the feed conditions and the flow rate of the feed. Feed temperature 25 degrees centigrade, feed pressure 25 bar, total feed flow rate 9205 kg per hour, and propane composition is 5.43% and propylene is 94.56%. This table shows the system or column configuration and specification. Column is the tray column, number of stages 241, feed stage is 156, condenser type is total condenser, reboiler is a partial reboiler. This table shows the operating data of the column. Column top pressure 24.5 bar, bottom pressure 25.5 bar, feed pressure 25 bar, feed temperature 25 degrees centigrade, distillate purity 99.5%, propylene slippage at bottom 5%. Let us now select the equilibrium model. K value equation of state. Equation of state model Peng-Robinson. Now solve the problem. Once the column has converged, optimization can be commenced. Shown here is the stream data for the feed, distillate product and bottom product obtained from the simulation results. Keep the feed and product flows and composition constant. Vary only the column pressure and see the changes in the reflux flow. So what are the observations? As the column pressure is decreased, the reflux flow decreases. As reflux flow is decreased, reboiler duty and condenser duty decreases. Results presented in the table 1 shows how the changes in column operating pressure is impacting the reflux flow requirement. This is the Motion energy balance for the propylene propane splitter at 25 bar. The reboiler duty is 6.447 megawatt and the condenser duty is 6.18 megawatt. That's a huge energy requirement. This is a mass and energy balance for the propylene propane splitter at 17 bar. The reboiler duty is 6.015 megawatt and the condenser duty is 5.89 megawatt. There is considerable drop in reboiler and condenser duty compared to the column operation at 25 bar. Let us now analyze the result in this table. As the pressure is decreased from 25 bar to 17 bar, the reflux flow is progressively reduced with a corresponding reduction in reboiler and condenser duties. At 25 bar, the reflux ratio is 9.1 and at 17 bar, the reflux ratio drops to 7.1. Likewise, the boil-up ratio drops from 214 approximately to 175. The condenser duty drops from 6.17 to 5.8 megawatt. Reboiler duty decreases from 6.44 megawatt to 6.01 megawatt. This is a graphical representation of the results obtained by simulation. As the reflux is reduced, the reboiler and condenser duty decreases. Approximately 0.43 megawatt of energy reduction is realized because of reduction of pressure. This corresponds to 6.7%. At rupees 3 per unit, the financial savings work out to approximately 100 lakhs per year. This is a significant amount of money. Another important factor to note is the impact of pressure reduction in K factor. The pressure reduction influences the quantity of propylene in the vapor phase of the propylene-propane mixer. Propylene-propane relative volatility increases with pressure decrease. This graph illustrates the K-value profile of propylene and propane at 25 bar across the stages obtained by simulation. This graph is a K-value profile for propylene and propane at 17 bar across the stages obtained by simulation. This plot is the effect of pressure reduction on propane-propylene equilibrium. The pressure cannot be decreased beyond a certain limit. As the pressure decreased, the column top temperature decreases. This is illustrated in this graph. The column top temperature at 25 bar is 58.1 degrees centigrade. The column top temperature at 17 bar is 41.12 degrees centigrade. Since the condenser uses cooling water, the limitation of lowest possible pressure is imposed by the available cooling water temperature. Typically, the cooling water supply temperature in the industry is 30 to 32 degrees centigrade and may be lower in the colder countries. To have sufficient driving force for heat transfer in the condenser as well as to keep the heat transfer area optimum, it is recommended not to reduce the pressure below 17 bar. Now we will see the impact of preheating in this case study. As discussed earlier, preheating of feed to the column is another way of optimizing the distillation process. In the above example, let us simulate the column with the feed entering the same feed stage but at a preheated condition. The revised data for simulation is the same except for the feed temperature, that is 55 degrees centigrade. The results of the simulation is shown in this table. At 25 degrees centigrade, reboiler duty is 6.447 megawatt. At 55 degrees centigrade, the reboiler duty drops to 6.25 megawatt. With feed preheating, you can achieve reduction of reboiler duty by 3%. This is a significant saving. We discussed earlier about the use of key ratio plot as one of the optimization methods. For the present case study example, this graph is an illustration of the key plot ratio. Note that the feed plate is placed at optimal location as indicated by the horizontal arrow. With this, we have come to the end of the presentation of part 1 of the 2-part series on optimization of distillation process. Hope this presentation with narration and animation was useful. Share with your friends and colleagues to reach out to large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing their knowledge base. Subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. Thank you for watching.